Our guest speaker, Steve Mensor from Achronix, right here.
All right. Ooh, all right. All right. I'll talk a little quieter. Thank you for being here. I'm going to talk about embedded FPGAs. So FPGAs that's delivered for SoC integration as IP. Okay. I'm going to give you a little history about our company, and then I'm going to mostly focus on the IP value proposition that we deliver. So the name of our IP is called Speedcore. And again, it is IP that can be embedded in your FPGA. To give a little context, Achronix has been around since 2004. Okay, so we've shipped multiple FPGA families as standalone chips. In 2015, we started engaging with companies to deliver IP as opposed to the standalone chips. We announced this to the marketplace in October of last year. The great announcement, we went to talk to everyone and said, basically, with our experience, we're taking that and bringing it to the SoC market, and I'll tell you why in a second. We presented this at ARM TechCon and won the award for Best Chip Product. To give you some context, I think it's really important. We're very focused on quality tool chains and quality FPGA architectures. Okay, it's an experience-based product, and I'll get in more detail about that. But ultimately, the end product has to be something that runs as fast as the established FPGAs, the leading-edge technology in terms of performance, area, power, etc. Okay, so why embedded FPGA? The first thing that people sometimes think is maybe I can save a little bit of money, or it might help with power, and it does. That's all good, but that's not why people are considering embedded FPGA. We're at an influx now. There is a massive disruption happening in terms of this artificial intelligence, machine learning. So what does that mean when you talk about machine learning? You're talking about massive data. So for example, if you think about autonomous cars, Brian Krasanich said the estimate is that each car will generate 4 terabytes of data per day per car. Okay, that's a massive amount of data, and that data is not simply being acquired. It's going to be thinking. It's going to be doing embedded vision. It's going to be doing sensor fusion. So it's a massive amount of computation. So you have a blend of very high data bandwidth and high compute requirements. Okay, so that's a problem. How do we solve problems? A CPU clustered system does many things very well, but what it doesn't do well is very high bandwidth computational requirements. So you need to have some type of accelerator, a parallel-based compute structure accelerator. There's different solutions out there. FPGAs are one solution. GPUs are another solution. FPGAs are basically a super high parallel structure. Okay, so they meet the requirement of high bandwidth. Secondly, is you need programmability. These algorithms are going to be changing for years to come, but probably decades to come. I saw a presentation over at ARM TechCon, or excuse me, Embedded Vision Summit, and they were talking about CNNs. And when you talk about CNNs, you're doing a learning process, and then you're identifying during the inference phase to see if I've got a match. And the match is a statistical hit. Did I get close? And one of the comments was, after you go through this whole calculations, and let's say you find an 82% chance that that's a human being. Okay, why? Why is it not 84? There's no understanding. It's basically just algorithms and best practices that are being implemented to figure out how to get better and better results. What that means is you need a programmable environment. You can't hard code these solutions into an ASIC. So you need programmability and you need the highly parallel. Okay, so let's just, for sake of argument, saying FPGA is a great solution. Now, how do you make your decision between an embedded FPGA versus a standalone FPGA? And there's many areas where, probably a majority of cases, where a standalone FPGA will be the optimal solution. You don't have the ASIC development. There's no cost for the IP. There's some inherent benefits, but there's very significant operational benefits if you do embed. So I'm going to talk about 2. In the upper left-hand corner here, we're showing a standalone FPGA that's got a PCI Express attached, and it's going to a CPU cluster. It can be whatever the CPU cluster structure is. If you want to transfer data across there, you're talking about a latency cycle that will be, it could be up to 10 milliseconds if you consider the software stack in the overall PCI Express chain. On the bottom left here, I'm showing, and by the way, I'm not making a statement about our product yet. I'm making general statements. If you have a chip that's talking through a PCI Express attached, you're going to have a latency delay. And if you have an embedded solution, regardless of what the technology is, you're going to have very low latency because it's going to be on the same. It can be on the bus. It can be connected directly to the CPUs. So in this case, 10 nanoseconds compared to 10 milliseconds, you're looking at a 1000x improvement. Every algorithm doesn't need low latency, but many algorithms do. So if you need low latency, you're talking about orders of magnitude improvement. So that's latency. The same thing holds true for bandwidth. There are many applications that are basically going to supply the maximum amount of bandwidth that chip can take for computational requirements. Again, this is not our company product. This is an inherent advantage of being embedded. You have direct connectivity from all of the ASIC into the structure. So if you come back to what I was talking in terms of acceleration applications, yeah, you have an environment where you need massive compute, you need high bandwidth, and you need programmability. So in those applications, and those applications are growing upon us in terms of machine learning, the embedded FPGA is the optimal solution. Okay, so in terms of Achronix, as I said, has been around since 2004. We are now very focused in this segment. We announced Speedcore in the end of last year. These are the type of applications that we are very focused in and where we're working with end customers. So first and foremost is machine learning, whether you're talking about data center or appliances in data center. What the companies that we're working with are looking to accelerate their CPU cluster applications for high performance machine learning implementations. I talked about automotive a bit. It's very interesting. The embedded implementation offers, obviously the value in terms of the high bandwidth, low latency functionality, but automotive has many characteristics that are challenging. One is there's a requirement at boot up that every device on the bus has to go out and do a self-test, and it has to basically say, I'm healthy, before it can be allowed to be part of the system. Most SoCs allocate about 15 to 20% of their SoC gates to the LBIST functionality. You don't have to do that if you have an embedded function. So above other purposes, you can be doing your LBIST through the FPGA. Another characteristic that's becoming more important is security. It is just inherently more secure to be on a single die solution versus being in a multi-die or on a bus environment. So a lot of interest in terms of automotive. 5G wireless is the first systems are going to be out in 2020 for demonstration, going into production in 2023. This is a massive redesign of the topology of wireless systems. You're talking about a 10x improvement in overall performance, a 100x reduction in latency, more compute pushed out to the edge with mobile edge compute. It's just a re-architecture completely. And with that, you're going to have the requirement to do massive acceleration, hardware-based acceleration. This is about 25% of the overall FPGA standalone market. So if you think about the $4.5 billion FPGA market, about 25% of that is wireless and will continue to be so. Network acceleration is your kind of deep packet inspection, pattern matching, I/O acceleration type of functionality. The two at the bottom, I think, are probably the most interesting. This is the appliances that I talked about a couple of seconds ago, where companies that we're working with are building specialty appliances for data center applications, where they're doing some type of acceleration for specific programs, SQL databases, some type of application acceleration, because, again, we're coming back to the high bandwidth requirements. So these areas are very focused on the embedded solution. In terms of our product offering, what we basically do is we have a modular architecture. And by the way, I'll step back for 1 second. The reason we offer embedded FPGAs is because that's what we do internally. When we build our FPGAs that are shipping in the marketplace, we go through a process that builds the core, and we have a separate engineering team in Bangalore, and they do the integration. So we have an architecture team in Santa Clara, and we basically go through a Speedcore implementation. We do the exact same thing for customers. So we have a tool, it's a little hard to see here. We basically go with the customer and say, what do you need? How much logic, how much memory, how many DSP blocks? You define it. And it will build that architecture, and it'll show you the area, how much power, configuration times, test times, etc. So it gives you all the dimensions. And those are trade-offs that you're going to have to make. It's almost like a memory compiler. If you want more functionality, you have to allocate more die area. We do work on we work right now on TSMC 16FF Plus, so that's where we're in production. Our technology is portable, so there is an effort to go through that, but it is portable, and we are having conversations with multiple foundries. There's a process that we go through, and it's a multi-month process, but we ultimately deliver that optimized piece of embedded FPGA IP, and what you get is a hard macro, so a GDS implementation, and you get a whole series of deliverables so that you can integrate it into your SoC. So, clearly timing files for doing your timing closure, power integrity models, signal integrity, characterization information, and so forth. So that's the chip side. But now you have programmability in your SoC. You need a tool chain. And our tool chain is called ACE, and we give you a specific version of that tool that works with your Speedcore. So now you have your SoC, you have an embedded FPGA in it, and it's just like a normal FPGA, it just has your SoC functionality with the programmability. It becomes a complete solution. In terms of our tools, so from an FPGA point of view, success and failure is completely dictated by the quality of the tools. The two big FPGA suppliers have very high quality tools. They do a great job. We've been in business, and as you can see over here, we started building our tools actually in about 2008, and this is showing all the different functions that we built over the years. Every single one of our implementations, when we work with companies, they want to do intensive benchmarks, and they want to verify that our capabilities of our FPGA technology are the same as leading edge FPGA technology capabilities. So we're, again, performance, area, utilization, power, compile times. Excuse me. There's videos on our website, or you can go to YouTube that give you just a brief kind of look at our tools. I think it's really important to note, and it's very hard to say because I'm self-promoting, but I wouldn't be at the company if our tools weren't good. I've been in the FPGA industry for my entire career, and the only way I know that they're good is from all of our customers and all of our benchmarks. People come back and say, wow, that's a high-quality tool chain. And again, that's an important part of this value proposition. Okay, so again, I've talked about Speedcore. It's shown in the center. This is kind of a depiction of dies and packages. So we do offer a standalone chipsets. They're called Speedster. Those are standalone FPGAs. Our current Speedster family is fairly mature. It came out in 2013. We also, at a recent announcement, talked about. Hold on one second. Yeah, so we talked about chiplets. So we didn't give a lot of detail, but what we are focused on when we talk to customers about embedded FPGAs, some customers say, that's fascinating, but can we get it as a die? It's specific for our needs, with a specific interface to talk to our SoC. So we are exploring and working with alpha customers to deliver 2.5D implementations of FPGAs. This is not like going to like the big FPGA vendors and saying, "Can you do die business?" This is 2.5. This is die built for 2.5D implementation for a package integrated solution. Okay. If you are interested to engage with Achronix, really, or any company, you're going to go through a massive benchmarking exercise. Nobody is going to put complex IP into their SoC on a whim. It has to work. It has to be successful. It has to hit their metrics. It's even more difficult than, let's say, doing an analysis on SerDes. And the reason is you don't know what's going to be in that FPGA. You have an idea. You know what the algorithms might be, but you don't know what they'll be changing to. So the due diligence is very intense. So when we work with companies, we have a suite of benchmarks, and we go through, and we can show them ours. But honestly, if anybody's seen benchmarks, you should never trust a vendor benchmark. I'm not trying to criticize. I'm just saying you should never trust a vendor benchmark, and nobody does. But they start off with this and say, okay, I see, if you look at LUT ratios, I see you're basically about the same as the established vendors. And you look at performance, okay, about the same. Then they got to start looking at their own designs. They need to do this for two reasons. One, again, they got to make sure it works. If it doesn't work, conversation's over. But more importantly, at some point they have to make a decision, how much FPGA do I put in? I know what my designs are. I need to know how many of your logic blocks are required, how many memory blocks, what type of functionality do I need so I can allocate that silicon area. So we go through pretty intense benchmarking. We're there. We're very confident in our tools. We're happy to give you an evaluation copy. You go do the evaluation on your own. We can supply an FAE if you want, a little help, or we can do benchmarks at our office. Any way that's preferred for the customer. Okay, in terms of, and I've kind of talked about this for a second. Excuse me. I do want to talk about quality of results. So in FPGA, I think it's going to be very much analogous to this artificial intelligence. The algorithms are just starting. The disruption in our lives, just from a personal point of view and a technology point of view and a company point of view, is going to be massive. And if you think about it, what's going to happen is there's going to be more and more adaptations of algorithms, new theorems, and so forth. And that's how things get better. There'll be improvements over time. That's exactly what happens in FPGAs. FPGAs are an algorithmic process. It's a place and route tool on an architecture. Both the architecture have to be optimized over multiple generations, as well as the tools. And so what we're kind of making a point here is, those little arrows at the top showing the customers, is the way you get good at FPGAs is you have a lot of companies that work with your products and quite frankly run into issues, and then you work with those issues and say, that's a problem that we have and we're going to get better. We're going to get faster. And when we make improvements, for example, to our software, we make a 1 or 2% improvement for each version that we release. Okay, that's not a lot, but if you start doing that on a long period of time, you get to a point where you have a lot, your performance is significantly higher. All of our tools support, our ACE tool supports all of our products. We do have, I'm not going to spend a lot of time talking about our board products, but again, built on the same technology, FPGA-based technology, and using the same tool chain. So that concludes my presentation. Again, we are, as a company, we've been around for 13 years. We did do an announcement last year. So we're private. We're not a public company. But we had a breakthrough year. This has been a fabulous year. We're going to do over $100 million this year. So we're established, and it's pretty exciting. But that most of that business is on our standalone FPGA business. If you look at our growth business, it's in Speedcore. It's in our embedded. So it's very interesting. I think it will have implications throughout the industry. And I think it will have, obviously, some very positive effects. So we're excited about it. Hopefully some of you folks are interested in it. And if you are, contact us at Achronix.